In the previous chapter, we have seen how to get the stress in beams. Now we will see how to get the deflection in beams because of the bending moment and shear forces. So to start the chapter, I take simple example of a cantilever beam. Cantilever beam is having a tip load of P, and it has length of L, and its Young's modulus is E. Now recall the formula of moment. It is called m upon I equal to C sigma upon Y equal to E upon R. Now in this equation we take these two terms now. So using these two terms we get m upon I is equal to E upon R. Here m is the bending moment at a particular location, I is the area moment of inertia of the cross section, E is the Young's modulus, and R is the radius of curvature of the beam at that particular location. So if we take a location x here at a distance of x from the free end, we can write this equation can be modified to get 1 upon r, and 1 upon r is given by d square y upon dx square, where y is the deflection in the y direction. Now obviously using this equation we can integrate it twice. So we integrate it once, we get dy by dx is equal to integration of m upon ei dx plus c1, where c1 is the integration constant, and again integrate it once more, we get this equation. So this is the method to get the deflection of the beams. Now let's solve a few problems. So first problem is this problem itself, wherein we have a cantilever beam with tip load of P and length L and Young's modulus E. So for this, how do we get a deflection? So recall that the bending moment at a particular location x from the from the fixed end is P L minus x. This is P into L minus x. So I substitute the value of P here, I get P L minus x upon EI is equal to d square y by dx square. Now this equation can be integrated, so I integrate it, so I get dy by dx is equal to P upon EI. This integration becomes Lx minus x square by 2 plus c1. This is minus. Now now you see at x equal to 0, which is a fixed end, there cannot be any slope because it is fixed in the wall. So the beam there is horizontal, so there is no slope there. So dy by dx is equal to 0 at x equal to 0. So I feed in this value here, I get c1 is equal to 0. Now I take the formula of diffraction slope alone, this much, and integrate it. So y is equal to P upon EI. This becomes L x square by 2 minus x cube by 6 plus c2. Now in this equation we know that at x equal to 0, which is a fixed end, there is no deflection. Y at x equal to 0 is equal to 0 because that's a fixed end. So that makes our c2 equal to 0. So the equation of y is y equal to P upon EI L x square by 2 minus x cube by 6. Now at x equal to L, we have the maximum deflection y max, which is equal to P upon EI. This becomes L into L square by this is L by 2 this x is L by 2, so L square by 4 minus L cube by 6 into 8. So that becomes P upon EI L cube by 8 minus L cube by 48. No, so sorry, this is 6. And this is 2. I think I have done something wrong here. So that becomes P upon EI L cube by 3. There is no 4 here. Now this equation is the equation of tip deflection of the cantilever beam where the load is applied at the end or the free end. Now this is a simple problem. Obviously we can have more complexity as we go ahead. So let's see a slightly more complex problem, which is that of a simply supported beam. Now how does a simply supported beam look like? It is like this. I'll just draw it. Simply supported beam is having a pin here and roller support here and a central downward force of P, where P is at the center, so the two halves are L by 2, L by 2. Now assuming that Young's modulus is E again, so I write the equation of the deflection. Now for this case, we know that the moment is Px by 2. So I get d square y by dx square is equal to Px by yci. I integrate this once, I get dy by dx is equal to Px square by 4ei plus c1. Now you see the beam will deflect like that. If I draw it once more, I will draw it here. This is P. The deflection happens like that. At this point, there is no slope because it is exactly the point where the beam deflection is maximum, and there the deflection starts decreasing. So at this point, there is no slope. So at x equal to L by 2, dy by dx is equal to 0. So I feed in this number here, I get dy by dx is equal to Px square by 4ei plus c1. So this is equal to 0. 0 is equal to P at L by 2 plus c1. So I get c1 is equal to minus PL square by, this is 16 ei. Now I just put the value here in the equation. I get dy by dx is equal to P upon 4 ei x minus PL square upon 16 ei. Now I integrate this once more. I get y is equal to P upon 4 ei into x cube by 3 minus PL square by 16 ei into x. Now you see this equation will have another constant of integration called C2, which can be found out by saying that at the ends here and here there is no deflection. So if I put the value of x equal to 0, I see y is equal to 0 there at this point. Y equal to 0 because that is a fixed end. So there I get 0. So C2 becomes 0 because in this equation this will become 0, this will become 0. So only this will remain. So this y equal to 0 means everything will become 0. So Ct is equal to 0. So my y will be equal to P upon 12 ei x cube minus PL square upon 16 ei into x. Now at x equal to L by 2, I have the maximum deflection y max, which is equal to P upon 12 EI into L by 2 का cube minus P L square by 16 EI multiplied by L by 2. 16. Now I solve this problem, or rather this particular expression. I get L cube by 8 minus P L cube by 32 EI. So this is nothing but P L cube by EI into 1 by 12 multiplied by 8 is 96 minus 1 upon 32, which is nothing but P L cube by EI into 32 is 3 times, rather 3 times 32 is 96, so it is 1 upon 96 minus 3 by 96, which is nothing but P L cube upon EI into 2 by 96, which is 1 by 48, or P L cube by 48 EI. That's the answer. Now this is a relatively complex problem. The reason is that here the slopes are 0 not at the ends, but the slope is 0 at the center point, because of which the constant of integration do not become both of them 0. C1 doesn't become 0 here, so it adds to an expression, because of which the equation becomes complex. Now this is still an easy problem. Now let's see a more complex problem. Now let's see this problem. This problem is like this. We have a cantilever beam. This is the third problem, and we have here a cantilever beam in which the force is not applied at the free end. Please remember this and be very, very careful now. It is applied at the center of the beam at distance L by 2 from the fixed end, and L by 2 distance is free, which means there is no load applied there. I apply a force P here, this is P. Now again, assuming that the Young's modulus is E, etc, etc. Now let us see how to get the deflection for this beam. But before we solve, let us see how this beam is going to behave under the force. So when the beam deflects, it becomes like this. The beam will deflect like that till the force is applied. Beyond that point, because there is no force, so that portion of the beam will simply rotate. So had this beam be free, it would have been like this. It rotates. This is a rotation about the force application point here. So this rotation is equal to the theta multiplied by radius. We know that the arc is equal to theta multiplied by radius. So I'll just say rotation arc is equal to theta multiplied by radius, where theta is the slope here. This is theta, and this is the radius. This is the radius, which is equal to L by 2. Now you see, we have to get the deflection here and add this portion to get a total deflection at this point. What is the deflection here? We can get it very easily from the previous case, which is, we know that the deflection at, let's say this point is A, at A is equal to P by 3 EI multiplied by the length till that point, which is L by 2 cube. So I get this P L cube by 8 multiplied by 3 is 24 EI. Now you see, this is the deflection of point A. Now point B, we have to get the slope at point A first. So the slope at point A we can get from the previous method, or we can integrate the equation. So how do we get this? How do we get this? What we do is, we again write the equation of curvature, which is m upon EI, which in this case is P upon EI L by 2 minus x, because in this case the force is applied at L by 2. Now I integrate this equation. I get dy by dx is equal to P upon EI L by 2x minus x square by 2 plus C1. Obviously C1 is 0, because at x equal to 0 the deflection is 0. So I get dy by dx at x equal to L by 2 at is equal to P upon EI, L by 2 multiplied by L by 2 minus L by 2 square by 2. This is that 2. So I get P upon EI L square by 4 minus L square by 8, which is nothing but PL square by 8 EI. This is the slope or theta A. So theta A is PL square by 8 EI. So the arc, the rotation arc, which means that the deflection at this point, above this point deflection, will be equal to delta B with respect to A is equal to theta A multiplied by the radius of rotation, which is nothing but PL square by 8 EI multiplied by L by 2, which is nothing but PL cube by 16 EI. I add this value to the value of deflection here. I get the total deflection at B is PL cube upon 24 EI plus PL cube upon 16 EI. This I simply resolve. This equation will become 1 by 24 plus 1 by 16, that is nothing but PL cube upon EI. Now I can just do a simple modification here. 16 is 2 by 3 of 24, so I can write this as 3 by 2 into 24, or I can simply solve this equation. It becomes I take out 8 common, so this becomes 1 by 3 plus 1 by 2, and that becomes 5 by 48 PL cube upon EI. That's the answer. So the tip deflection at the point B is 5 by 48 of PL cube upon EI. Now you see, this problem is a relatively complex problem. Actually, this is a very complex problem, I'll say. The simple reason being, here we need not only need the value of the what should I say? Not only need the value of the deflection, but also we need to have the value of the slope. The slope now, what happens because of the slope? See, slope causes the rotation, and because this problem is relatively simple right now still, because we are applying the force at the center, the force can be applied anywhere through the length. So we have to be very careful that we get the deflection only till that point where the force is applied using the bending moment formula. Beyond that, we have to get the deflection by multiplying the slope and the radius. Now let us solve one more very complex problem. Now this problem is actually quite complex, I'll say, and this is the kind of problem which you can expect in GATE and other competitive examinations in almost all branches of engineering, whether it's mechanical or civil or aerospace. What happens here is we have a beam, a cantilever beam with an end force P. So what is the big deal? It's very easy, right? The problem is not that easy because now the I is not constant. It is not a constant. In this case, the thickness of the beam remains constant. It is like this. This is L and this is T. But the width is not constant now. So if I see from the top, I will see that this is the wall and the width is like this. It is maximum width here B drops down to 0 here in the length L. This is a very practical problem actually, and let us see why it is a practical problem. So if you remember an aircraft, now the aircraft wings are like this only. That the wings are not constant in width. They are the maximum where they are attached to the body of the aircraft, and they drop down to a smaller number at the tips or the ends. So this is exactly the same problem which is from the wing design. So how do we solve for this problem now? So this is the width. Now I take the problem here, P, and this is the fixed end, and at a particular location X from the fixed end I find out what is the moment. So the moment is P L minus X. See, the moment doesn't change because of the change in moment of inertia, because moment is caused by the load alone and the length. But the deflection equation, d square y by dx square is equal to m upon ei. Here we have two variables, m and I. So I at that location x will be equal to 1 upon 12 the width there, bx multiplied by t cube. So what is the bx value? What is the width at location x? This is the location x. So bx is nothing but b, the maximum, 1 minus x upon L, because it is linearly changing. So you see the equation of or the variation of x being linear, it drops down from maximum value of b to 0 at the free end or at the load end. So I put this value in ix, I get ix equal to 1 upon 12 bt cube into 1 minus x upon L, or 1 upon 12 bt cube upon L minus x. Now I feed in this value in the equation, I get d square y upon dx square is equal to m upon ei, where m is p L minus x upon e into the equation of ix, which is 1 upon 12 bt cube by L into L minus x. Now I solve this equation. L minus x and L minus x is a constant, so it is cancelled out from the equation, and I get 12 PL upon EBD cube. Now this is D. So you see the slope, or rather the curvature, is a constant now. That's a good thing, because the curvature constant means it's a circle. Now I integrate this equation once, I get dy by dx is equal to 12 PL upon EBT cube into x plus C1. Over here 12 PL EBT, everything is a constant, so we can put this as a constant called k. I just put this here, I get kx plus C1, where k is equal to 12 PL upon EBT cube. Now the C1 is equal to 0 because this is a cantilever beam, so dy by dx is kx, and I integrate it again, I get y equal to kx square by 2 plus C2. Again at x equal to 0 there is no deflection, so C2 is equal to 0. So y is kx square by 2, at x equal to L, y equal to k L square by 2, which is nothing but, I feed in the value of k, it becomes 6 PL upon EBT cube. Now recall the value of deflection for the cantilever beam, which was of constant cross section, so that was PL cube upon 3EI, which is nothing but PL cube upon 3E into 1 upon 12 BT cube, right? So that becomes 4 PL cube upon E bt cube. This is cube. So you see the ratio of the deflection of tapered to the constant cross section beam deflections is 6/4, which is 3/2. So which directly tells us that, obviously, I mean, it is intuitively also clear that because we are reducing the area of cross section, so the deflection is more, but it is more by 50%. So had we had got a beam which was constant cross section beam, we would have got a deflection of y constant. But in this tapered case, where the beam width is changing from whatever width is there for the constant cross section beam to 0, we get a deflection which is only 50% higher. Now in this case, had this beam been of constant cross section, it would have been like this, correct? So we reduce the beam weight or mass by 50% and the deflection increases by 50%. So there is a trade-off. The deflection increase results in decrease in mass. So we have to get to a trade-off as to what kind of mass we want to save vis-a-vis what kind of deflection we can have. This is a very important problem in wing design, where the deflection normally is not the main criteria. It is basically the mass or the weight of the aircraft which is more important there. Obviously, we cannot have a deflection which is too high also. So we go to a trade-off by seeing what is the deflection which we get compared to the mass which we have for the wing, and we reduce the mass to as much less value as possible, keeping the deflection also in check. But the way they solve is exactly this way only. So I request everyone to solve more such problems where only the moment is not changing, but also the I value is changing, and because the change of I increases the complexity many times, there's a geometrical change there. So these kind of problems provide a much bigger insight into the whole theory and the formula of the deflection of the beams.